Welcome to this tutorial on how to set up the Planetary Processing server-side backend. Let's start by going to the Planetary Processing website at planetaryprocessing.com. Create an account by clicking Get Started, then input the email you want to use to manage your game. A verification email will be sent to you to set up your account password. If you already have an account, you can just click Login. Once you're logged in, you can create a new game from the Game section of the dashboard. Name your game and your repository where the game code will be stored. Chunks are the segments which make up our game world. Start with a chunk size at 64. You can change this later once you know more about chunks. Though, if you're planning on integrating with Unreal Engine 5, we would recommend starting off much larger, using 64,000 as a base size. When you create a new game, you will be shown the command to download that game from the server repository. The server repository is where all of your game world's code is stored and processed. Both the repository address and your game's ID will always be accessible and can be easily copied from this page. On the new game page, you can copy the entire git clone command and navigate to wherever you want to save your game on your computer. Either open a terminal from that directory or search for an equivalent application on your computer and navigate to the folder using the cd command. Paste and enter the git clone command to download the default server-side demo code for your new game. The first time you do this, you'll be prompted to enter your Planetary Processing email and password. Be aware that some terminals will hide your password completely as you enter it. Simply enter your password as normal and press enter. Your folder should now have a directory with the same name as your repo. Inside, we will find the standard structure of a server-side game. There will be a hidden.git folder for managing version history, an init.lua file, and another folder for entity Lua files. The entity Lua files define how objects and creatures behave in your game. If I open each of them up briefly, you can see what the default demo code looks like at a glance. The demo creates a basic open world game for a player in a forest inhabited by cats. We are not going to worry about this code for the moment because we're going to be creating a world from scratch. Cut and paste the init.lua file and the entity folder somewhere safe for later reference, or delete them completely if you're feeling confident. Now we're going to re-upload our empty repo back to the game server. Turn to your terminal and use the cd command followed by the name of your repo to navigate inside our game repository. Then use the command git add-A to move our changes to git staging. Staging allows you to review your code before it gets uploaded. Use the command git status to check the correct files have been changed. In this case, they've all been deleted. Now that we've confirmed everything is correct, we can record our changes in the game's development history, using git commit-m and the message empty repo. Then we upload them to the online repository using git push. If we return to our game dashboard, we can deploy our changes to make them run on a live game server. Let's use the deploy latest button to load our code onto the server, and then start game to try and run the empty repository. When you first launch your game, the map of your world will display. Currently there are no entities or players inhabiting the world, so nothing is being processed except the fundamental chunks dividing up our world space. If we go into the game's logs, we can learn a bit more about what our world needs. Open logs in a separate tab and select your game from the drop-down. The logs will show any errors or print statements from your server code. To better handle a large amount of logging, logs are placed together in log groups. These indicate which logs happened within a certain time frame, so it's easier to pinpoint a log from a specific moment. Logs will tell you which of our world chunks has sent a message. In this case, each chunk is sending the same 3 error messages when they are created. For example, the chunk at position -64 says there is no Lua code in our repository to process, since we are missing both the init file, which initializes chunks, and the entities folder for processing entity files. So let's return to our codebase and add the minimal possible requirements to resolve our repository errors. Make an entity folder, and within it create a cat.lua file to represent one of our entities. Then at the top level, create an init.lua file to initialize our chunks properly. Open this init file and give it its own init function, so that the server has code to process. We'll start with just an empty function. Make sure to save it and repeat the process of staging, committing, and pushing the changes to the Git repository. Most terminals allow you to use the up arrow on your keyboard as a shortcut to cycle through your recent commands, rather than retyping them each time. However, this time we're going to deploy the repository to our active game slightly differently. First, stop your game. Then, deploy the latest version as before. We've stopped it because we want to make fundamental changes to how our chunks load. Whenever you want to test a change which alters how chunks are initialized, you should reset the simulation state to start the world afresh. The same can be said of any changes to entities. It is worth using the Wipe Entities button to clear any characters running old code. Start up your game again, and when we check the logs this time, we can see that the timestamp hasn't changed on the log group, because there are no new error messages. Our world is now in a stable state, so let's learn a bit more about it. We have briefly mentioned the term chunks. Chunks refers to the separation of your expansive world into more manageable cuboid sections. They appear as squares on the game map. Chunks act independently, but players and entities can move from one to another seamlessly. Each chunk of the world runs the init function in the init file, building your game world like a jigsaw. We are going to look at the properties of chunks more closely by logging them as each chunk is created. Each chunk has 5 attributes. Its X, Y, size, generated, and dimension properties. All this piece of code is going to do is print these values for each chunk, so that we can better understand each field in more detail. Save the init file and redeploy. You can see we now have a new log group for a different time period. Each of our loaded chunks is printing its properties as it is generated and loaded. The X and Y values are the chunk's coordinates relative to the central chunk. These chunk coordinates will always be an integer. This chunk at the center has an X and Y of 0. This one has an X and Y of 1. And this one has an X of 1 and a Y of 2. You may notice that these values don't match up with the axes on our map. That is because these axes refer to world coordinates rather than chunk coordinates. To better explain this, we can return to our logs and look at our next property, chunk size. Every chunk in your world is the same size, in this case 64 world units. The size field refers to both its length and width, since all chunks are perfect squares. Chunk size can be adjusted in the settings section of the dashboard. Our next property is the generated field. Any chunk which has never been loaded will be false, but it becomes true once it has been loaded at least once. Generated chunks appear as light grey on the map. However, a generated chunk is not the same as an active chunk. If we click into a chunk on our map individually, for example this one, we see it is inactive and not currently loaded. Nevertheless, its generated value would be true because it has been loaded at least once before. Once we add entities, it will be much clearer which generated chunks are active and which ones are inactive. Unloaded and ungenerated chunks will appear as dark grey on the world map. It is good practice to use a NotGenerated check inside your init function. This makes it so that the chunk's init function will only trigger once, the first time it is generated and loaded. This is useful since chunks may reload sporadically in response to nearby chunk loading entities or players with poor connection. Our final chunk property is dimension, which is by default an empty string. The dimensions feature allows you to have multiple worlds within the same game server. For a chunk, the dimensions property indicates what game world, lobby, or match your chunk is in. You can view different worlds by selecting them from the dimensions dropdown on the game dashboard map. Currently, we only have the default dimension. As a general rule, it's best to treat the chunk fields as read-only, since if you try to change the size by setting the chunk.size value, for example, it would not affect the actual chunks or world coordinates of the map. It must be updated in the game settings. That about covers our chunks, which make up our game world. Now let's move on to the entity behaviors within it. Open up your cat.lua file, and we will give it a basic entity template. Much like the chunk, the entity has an init function, so that we can define its properties when it's first created. The parameter self refers to the object itself, in this case, a cat. For instance, you might define the health of cats by creating a health attribute in its data field. The update function runs code every tick of the game world. A tick is the measurement of time for how many times a second the code tries to run. The default tick rate is 10, so the update function tries to run every 0.1 seconds. It can be altered in the settings tab of your game dashboard. The update function is useful for any continuously updating code, like a walking script. The self parameter is once again self-referential to the cat object. The dt parameter, however, is the time in seconds between each update function, because this can vary between faster and slower machines. Multiplying movement and other update scripts by the dt parameter helps to standardize them. It applies either a handicap to values processed on a faster machine or an advantage to values processed on a slower one. This helps the values match the amount of time which has actually passed rather than being skewed by the machine's processing speed. For instance, you might start a movement script by multiplying your speed by dt. Then apply that handicap speed to your positional xyz values. The entity's message function receives messages and executes code in response. These messages can come from either another entity on the server or from the game client. Once again, their first parameter is self-referential, and their second parameter stores the message which has been received. Each message has a minimum of 2 fields: a data field, which is the main content of the message. This contains a key value Lua table with the information being sent, and a client field, which will be set to true if the message is coming from a player's client app, or false if it's coming from another server entity. We will practice some message code shortly. Finally, all these functions, init, update, and message, must be stored in a table like so and returned. This allows the game server's processor to see and run them from anywhere. Let's spawn a cat entity into our game world so that we can see a basic entity in action. Go to your init.lua file and use the API function api.entity.create to make a cat. We have to define some of its fields, such as its type being a cat, its position being 000, and its current data store being an empty table. We are going to do the same as we did with our chunk. When the cat spawns, print out all the properties of each entity. Like the chunk, the entity has 5 exposed properties, which we can look at in the logs. Save the cat file and deploy. Now we can see our cats on the world map at 000. They are all stacked up on top of each other, but we can see how many currently active entities there are in the world by looking at the bottom right-hand panel. Refresh our logs and we can see a new log group displaying our cat properties. Each entity has an ID to identify it. If you have multiple of the same type of entity, such as a cat, the ID will be unique to each. They are generated in a standard UUID format of 8 characters, followed by 3 groups of 4, then a group of 12. The type field allows you to define entities with the same behavior. This is because the type field matches the name of the Lua file in the entity folder of your game repository, in this case cat. Different entity types can be displayed and counted using different colored icons on the map. The type is the main way an entity is identified to the client-side game engine during development. The data field is a fully customizable Lua table, which can be used to define whatever properties you want your entity to have. For instance, self.data.health equals 34 creates the health property in the data field and assigns it the value 34. But by default, it's an empty table. The chunk loader property defines whether an entity should cause chunks to generate in a 3x3 grid around it. By default, this is false for most entities, except for player entities for which it is forcefully enabled. This helps improve performance by only loading the parts of the world which the players are actively engaged with or near to. Non-player chunk loader entities are a premium feature. Here, the cats are not chunk loaders but happen to be in the center of the world, which itself temporarily acts as a chunk loader when you start your game. So we have a 3x3 grid of actively loaded chunks around the center, and a total grid of 5x5 light grey chunks which have been generated at some point. Finally, we have transients. Transient entities will despawn if the chunk containing them is unloaded. For example, if these cats were transient and in this top right hand corner of the 3x3 loaded chunk grid, they would all become removed once the chunk became inactive, even if the chunk were to be loaded again. So, to reiterate our api.entity.create function, the cat string is the entity's type, followed by its x, y, and z coordinates, and the empty table corresponds to the customizable table in the cat's data field. The create function also returns the created entity, so we could duplicate our print code from within the chunk's init function to see the cat properties that way. Since the logs would be identical, instead of deploying this, we're going to use our cat variable to send a message, Comment out the print code and add the API function api.entity.message to the file. We are going to send a message to our cats using each cat's ID field and alert them that the event earthquake has occurred. Your message can be any sort of Lua table. Save the init file, and next we're going to update our cat.lua file to react to this message. Comment out the print attributes code. Now whenever the cat receives a message to its message function, we check to see whether the message data has an event field set to earthquake. If so, our cats are all going to react to the earthquake by saying meow. Save the cat.lua file and redeploy. If we visit the logs now, each of our cats is logging a meow as the chunks are loaded. We can expand on this and start giving our cats more options than just meowing when they learn there's an earthquake. To start exploring entity activities a bit more, let's make it clearer which cat is being created by which chunk. Return to the init.lua file and restructure the cat creation function. Create a check to only spawn cats in the default dimension. Then adjust the creation function's x and y parameters. Multiplying the chunk's x value by its size will position the cat in the bottom left corner of the chunk which spawned it, and adding half the chunk's size again will center it in the middle of the chunk. The process is the same for the Y position. Our Z position and data table can remain the same, and so can our message. Save the init.lua file and redeploy. Now it is very clear which chunk is creating which cat. The cats appear grayed out in chunks which have been generated, but have been unloaded and are now inactive to save resources. Since we can see individual entities now, let's have our cats start acting in response to the earthquakes more visibly. Return to cat.lua and make a table of reactions for the cats to do in response to the earthquake. We have a total of 6 possible reactions, each using a different entity function. Our first is run, using the self::move function. The move function will reposition the cat a set amount along the x, y, and z axes, relative to its current position. Typically this function is used inside an update function, to act as the motion or step a character does at each moment. Our second reaction, teleport, uses the self::move_to function. This could similarly be used in an update function for movement, but its xyz parameters are instead world coordinates, since they are calculated relative to the world's origin rather than the entity's current position. Our third reaction, assess, uses the self::getPosition function. This is just an informative function which returns a Lua table of the entity's x, y, and z world positions. Our fourth reaction, leave, uses the self::remove function. This simply deletes the entity calling the function. Our fifth function, look around, uses the self::getNearbyEntity function. This gets a list of entities in a certain range. In this case, it's trying to get any within 3 chunks distance, which is approximately its maximum, since it will only reliably check for entities in chunks adjacent to it. Finally, change dimension uses the self::warp function. In order to move to another dimension, we must first create one using the dimensions API. This API can create dimensions, remove them, or provide a long list of existing dimensions. The warp function teleports the entity to a specific location, but in another dimension, using the name of the dimension followed by the xyz world coordinates, similar to the move_to function. We want our cats to react differently, each using one of the functions from this list. So in our message function, we create an array of keys from our cat reactions table, which is the list of strings, run, teleport, assess, leave, etc. Note that the Lua environment the server runs puts limitations on certain libraries, including the OS, IO, JIT, table, package, and coroutine libraries. So instead of using the table library's regular insert function, we must instead use the table API to append these reactions to our list. Also note that the api.table.append function only returns a changed table, which must be saved into a variable. It does not alter the original table autonomously. With this new single-column table, cat reaction keys, we can use math.random to pick one of the reactions from the list. For instance, the reaction change dimension might be randomly selected and stored in the data field of our entity. We don't strictly need to use the self.table here, because we will be using the reaction information immediately. But let's just assume that at some point later we will need to know how each cat reacted to the earthquake, so we'll save this knowledge as part of the cat object. In the short term, we can use this random reaction name as a key for accessing a random function from the reactions table. Make sure when you use a function from a table like this to remember to pass the cat's self object through as a parameter so that the function's code can access the cat itself. Save your cat.lua file and redeploy. On the map, we can see the cats update in real time as the earthquake message hits. The cat created in our central chunk ran when the earthquake happened, putting it slightly off center by 16 units. It also now shares its chunk with any cats who teleported to the world coordinate 1616. If we look closer at the chunk, we can see that 5 of them have stacked up there, leaving their original chunks empty. Any cats which have remained in the center of their chunk could be assessing their position or looking around at neighboring cats. We can look at the logs in a moment to check. The abandoned empty chunks could be from cats which have teleported into the center, but they could also be from ones which decided to leave, or any which warped to another dimension. If we now check our logs, we can see what information our stationary cats have gathered. As it turns out, only one of them was looking at other nearby cats. It's returned a list of 3 cat entity objects it can see. Since we didn't do any additional formatting to get their fields or IDs, the log just displays the memory address locations of their tables. The other stationary cats have all printed their world coordinate positions as XYZ values. If we return to our map, we can also swap the world view to our no earthquakes dimension and see that one cat did swap dimensions entirely to escape the earthquake. So now we have a working simulation of cats in an earthquake scenario. But how do we interact with this to make it a game? All inputs from the client, from the person actually playing the game, must be sent to a player entity's message receiver function. We don't currently have a player entity, so let's make one. Players are the same as any other entities, apart from a few key aspects. Fundamentally, they use the same 3 functions: init, update, and message. However, a player's chunk loader property is always overridden to true, so each player generates a 3x3 grid of chunks around them. When first starting out, it's worth adding a comment to this effect as a reminder. You will also want to add a message.clientCheck to your message receiving function to distinguish player movement sent by the game client from any messages sent from server entities. A typical player movement message contains a table in its data field, using X, Y, and Z as key attributes, each with values for how far the player should move between each message. If you're using the move_to function instead of the move function, the X, Y, Z values will just be the entity's updated world coordinates. The principle of sending messages to the game server is the same regardless of which game engine you're developing in. You will always use your established server connection to send through a table, map, or dictionary, in the same key value format we have seen for the server entity messaging. In Unity, you send a dictionary through the pp master component. In Godot, you send a dictionary through the pp root node. In default, you send a Lua table via the game object which has the pp master component. In LÖVE2D, you send a Lua table through the SDK. In Unreal, you send a tmap or JSON object through the Planetary Processing instance. You may have noticed that the XYZ table keys shown here don't always match up with the game engine's positional values. This is because every game engine has different world axes. It is worth taking a moment to see how your chosen game engine's world coordinates translate to the Planetary Processing multiplayer engine, so that the game dashboard map matches your client-side world. If you are planning to send lots of positions back and forth, create a function to do the conversion easily so you don't get caught out. Every input and incoming message from the game client is received by the player.lua file. This will mostly be player movements and actions. Any messages from the client to non-player entities have to be relayed via the player.lua file, using the api.entity.message function. If we now deploy this to the game server, any game engine client with cats and players set up correctly will be able to join and explore the world. If I run a game from Unity, Default, Godot, Unreal, or LÖVE2D, the player will appear on the map and be able to move around. And because they are a chunk loader, they will generate new chunks as they move, which will trigger fresh earthquakes for the newly spawned cats inside them. So now we have a working multiplayer game server which players can connect to. To make more changes to your chunk and entity behavior, you can combine and build on any of the functions in our cat reactions. Or if you want to add more player interactions, start setting up messages between them and other entities. Our documentation has all the details on the entity and API functions available for crafting your game. Thanks for watching this tutorial on the Planetary Processing server-side backend. Check out our other tutorials on how to set up the client-side part of your game in your game engine of choice. If you want to stay up to date on everything we do, or need help, check out our Discord.